Hi everybody. Today we're going to talk about how scaling affects perimeter as well as area and what happens when we start looking at them and comparing. And we're going to start out first of all with a rectangle. We're going to then progress to a triangle and look at some of the things that happen. We're going to start out pretty easy. We're going to begin with a rectangle that is 4 by 6. In other words, it's 4 units across and 6 units in height. We're going to, on another piece of grid paper, draw a rectangle with side lengths that are twice as long as that, labeling the new vertices as E, F, G, and H. And we're also going to draw a rectangle with side lengths half as long, and they're going to be labeled with vertices I, J, K, and L. So when we talk about this, we can notice that this original one, as I said, it's 4 across and it is 6 vertically. That means that I want something that's doubled that. Well, twice as long means multiply everything by 2. Excuse me. And when we multiply everything by 2, we are going to then have definitely a bigger rectangle. So this would be times 2, which would be 12. This would be times 2, which is 8. So I'm just going to start up here with a rectangle that is going to be 1, 2, 3, 4, 5, 6, 7, 8 wide, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 long. Now because it is a rectangle, we know that the opposite sides are the exact same lengths. So that's 12, that's 8. So we have something that is 12 by 8. It did tell us though to label the sides, and what we're going to do is we're going to make them corresponding. So since we begin here with A, then B, then C, then D, we're going to start in the same bottom left-hand corner with E, go across to F, up to G, and then over to H. When we look at this, we can see that it is twice as wide, twice as tall. We're going to do our other one also on the same grid paper, half as long. Well, half of 4 would be 2, half of 6 would be 3. So I'm going to draw one that is 3 and 2, and then 3 and 2. And it says to label these vertices, we're going to go in the same corresponding directions. We're going to start down here with I, then J, then K, and L. And this is 2, this is 3, as we can see. Those sides are going to be important to us later on when we start talking about making some comparisons. As we look at our questions here, and feel free to pause this at any point in time to catch up with the drawing or to write the questions and the responses. Our first question says, describe the method you use to double the length of each side. Oh, that was easy. Double and twice mean the same thing. So all we did was we multiply the lengths by 2. What did we do to get each side half the length? Well, we multiply the lengths by 1/2. Now some of you might say, well, isn't that the same as dividing by 2? And yes, it is. But remember, when we're talking about scale factor, we need it to be a multiple, not a division. And that's going back to previous information that we've had. Our next question says, do you think the area of the new rectangles change at the same rate as the sides? Well, we can look at that in a couple of different ways. We can look at it as what are the areas, and remember the area is the interior, it would be how many squares are inside there. If we were to count this, we would be saying 4, 8, 12, 16, 20, 24. That there are 24 squares inside. We could get that also, as you know, by multiplying the length of 6 times the width of 4. 6 times 4 is 24. We could sit there and count all of those squares, but it's going to be much faster if I just multiply and say, oh, 8 times 12, that's easy. That would be 96. And the other one, well, it is easy to count. 1, 2, 3, 4, 5, 6, or 2 times 3 is 6. As we look at those, notice there's a little bit different relationship coming up here. So if we're thinking about area, and our question says, do you think the area of the new rectangles change at the same rate? Remember, a rate is a ratio. Is it going to be the same as doubling it or halving it? Well, it doesn't look like it, because if I were to double 24, I would get 48. Yeah, 96 is quite a bit bigger. If I were to half 12, or half 24, I would get 12, and 12 is bigger than 6. So there's something else going on here. So if we're just looking at that, we could immediately say that in answer to this, no. And the reason we would explain is we can see from the areas that they are not the same as the lengths. So they're not the same rate of change. And we talked about rate of change when we were talking about proportions, percents of change. So this kind of takes us back to a little bit of what is that proportional thing? Remember, when we talked about scale factor is a ratio. Scale factor is a rate of change. And so all of those tie in together. As we look at our next thing, we're actually going to put this into a table format that might make it a little easier to start seeing some other relationships. We're going to talk about perimeter, the perimeter scale, area, and the area scale factor. So if we look at the rectangles, the new perimeters and the old perimeters, our perimeter of our original, which was 4, 6, 4, and 6, we have the sum of the sides, so 4 plus 6 plus 4 plus 6 ends up being 20. Our twice the size, however, if we look back at it, that one was 8, 12, 8, 12. What happens when I add 8 plus 12 plus 8 plus 12? I get, whoops, everything moves, sorry about that. I get 40. And what about my smaller rectangle? That was 2, 3, 2, 3. So when I add 2 plus 3 plus 2 plus 3, I get 10. Our scale factor, okay, from A, B, C, D, if we look at it as a ratio, well, we're talking about the original to the new is 1 to 1. If we talk about it as a ratio in fraction form, we're going to put the new over the original, so the new over the original, but here is still 1 to 1. So our scale factor is 1. If we're talking about our original compared to our new, everything in length was twice the size. If we write this as a fraction, that would be the new over the original, and we get a scale factor of 2. Remember, we multiplied everything by 2. If we're talking about this one, well, we would be talking about half the size. We would be talking about 1/2 to 1, or 1, more importantly, 1 to 1/2. When we talk about 1 to 1/2, that would be 1/2 over 1, which is a scale factor of 1/2. That's what we multiplied by, if you remember, in the original problem. Now we can also look at these as, well, what is it to the perimeter? Well, in this case, I could instead write that the perimeter is 20 to 20. Oh, or 20 over 20. This one would be 20 to 40, or 40 over 20, which is still 2. If I did this, it would be 10 as the new and 20 as the old. If I write it in fraction form, it's 10 to 20, which is 1/2. We can see that it still works even with perimeter, the same as what it was with the sides. But if we start looking at area, remember, length times width, talked about it on the previous thing. The area of our original rectangle was 24. Of our bigger rectangle, sorry, I think I said triangle, our bigger rectangle was 96, and our smaller rectangle was 6. If we look at those and put them in a ratio of new to old in fraction form, think about what happens. Well, it is itself, so it's still a scale factor of 1. 1 times itself is 1. However, this one, I would be putting the new and bigger one over my original, which is 24. Oh, how many 24s fit into 96? Actually, that's 4. And if I did this one as the ratio of the new to the original, oh, smaller numerator, 6 24ths, I can simplify that to being 1/4. Do we see any kind of patterning going on here? I double the sides, it's 4 times the area. I half the size, it's 1/4 the area. Let's think about that one. What went on? Oh, could it be because the area is affected by both the length and the width, that doubling both directions actually is like multiplying by 4, and cutting each direction in half is like taking half and half? Oh, 1/2 times 1/2 is 1/4. They're squaring. If you can remember what squaring means, it means multiplying a value by itself. Let's see. That's kind of interesting with rectangles. Is it going to happen with other figures? Well, we're going to try that same kind of thing with a triangle. Now, as we're making a triangle, we're going to try and do this so that we are doubling it, twice the size, and having it half the size. When we do that, working with a triangle, there are a lot of different aspects to it. One thing that we notice, I hope, is that this one actually follows on one of the grid lines. It's very easy to decide what its size is. We can count 1, 2, 3, 4, 5, 6, 7, 8. All right, that's not too tough. It's 8. Well, if I'm going to take that side, which is 8, and double it, it's going to be 16. So that's going to be fairly easy to figure out, going 16. So I'm just going to start here, and I'm just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, whoa, 16. Well, way over there. The other sides, it's like, how am I going to figure that out? Well, you can do this in a couple of ways. You can look at this and say, well, C is 2 spaces over. I'm going to double that width. So I'm going to start 4 spaces over, and then this is 1, 2, 3, 4 spaces up. So I'm going to double that and go up 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to draw straight down. Now, if I did this perfectly, I can actually do something like this. I'm going to take my fingers and say, all right, there's that. Up, I put it there, I put it there. Oh, 2 of them fit. I did this perfectly. There's how to do that. Now the third side, that's easy on a triangle. All you do is connect the points. And by the way, if I were to take this over here, up, there's the middle, there, I come back, yes, it's the same size. Funny thing. I'm now going to label those corresponding just like I did there. This is going to be D, E corresponds with B, and F corresponds with C. Pretty simple. I'm going to also draw one half the size. That means I'm going to take them in halfway. So, since this was 8, I'm going to make a side that is only 4. Now remember, we said this was over 2 before it went up. I'm instead only going to go half of that, which is over 1. This went up 4. I'm just going to go up 2 and bring that down, bring that over. If I did that perfectly, this side should be exactly half of that, and guess what? 2 of the smaller one fit there. It worked out perfectly. I'm now going to label that as G, H, and I. Now remember, there's some other important things, not just the base. The base on this one is 16. The base on this one is 4. But remember when you were working with triangles, height was another thing. And so we're going to look at the height here. This height is 4 from the base to the highest point. On this one, from the base to the highest point, that's 8. And here, from the base to the highest point is 2. And we can see 8 doubled is 16, 4 doubled is 8, half of 8 is 4, half of 4 is 2. So it's pretty easy to do triangles as well. Now notice we don't have any questions on this one, but we do have a table on the next slide. So keep in mind those values. As we move over to our slide, this one looks a little bit different. Feel free to pause it and write down your values as we go. Notice it talks about our original triangle, our triangle that's twice the size, and our triangle that is half the size. We're going to look at a new word called dimensions. Dimensions are really the length and the width, or the base and the height, as we're looking at this. When we look at our dimensions for this original triangle, remember, across the bottom, our base was 8, and going up from the base to point C was 4. In ours that was twice the size, across the bottom we drew 16 squares, and going up the height we discovered was 8. On our half the size one, we drew a base that was 4 squares, and we saw that going up the height was 2. Now when we look at these, the ratio from ABC, the ratio from ABC, this is, if we're going to, might as well write it as a regular ratio, we could write it as a 1-to-1 relationship. Or we could put it as 1-to-1. This one, we could put it as 1-to-2, because we doubled it. We could write it as 2-to-1. We could look at the difference in our sizes and say something like 16 is to 8 as 8 is to 4. All of those end up being 2-to-1. We're talking equivalent ratios. And if we're talking about half the size, well, that would be going from 1 to 1/2 of its size. If we're looking at these in ratios and we were to compare this way, it would be doing something like this. 4 is to 8, 2 is to 4, and if we did this, we would be putting 1/2 over 1, which we all know is the same as 1/2. Now we can also look at these as these are our scale factor. So if we wanted to also include this as the scale factor, we would say that this has a scale factor of 1, this has a scale factor of 2, and this has a scale factor of 1/2. Area now, if you remember to find area, area is actually half of the base times the height. 1/2 base times height. Because remember back, when we're looking at rectangles, you cut a rectangle in half, you get a triangle. So if we multiply the base and the height, or the length and the width, to get a rectangle, and a triangle is half that, that's why we have half of the base and the height. So if I were to find the area, I would simply say half the base is 4, times it by the height of 4, and I'm going to get 16. Here, half the base is 8, times it by the height, and I'm going to get 64. Half the base is 2, times it by 2 of the height, and I'm going to get 4. When we look at our area scale factor, and we're looking from the original triangle ABC, look at what's going on. Here, this would be 16 is to 16, meaning it is 1, meaning it's the same size. Here, however, our scale factor is 64 to 16. What happened there? Oh, if I simplify 64 to 16, I'm going to get 4. This scale factor is 4, meaning it is 4 times the size, right? Here, if I take my 4 and put it over 16, oh, that's 1/4. My scale factor means it is 1/4 the size. Now remember, we talked about this happened on our rectangles. When we doubled the lengths, the area became 4 times. When we halved the lengths, the area became 1/4 the size of it. The relationship here is whatever you do to the lengths, you multiply it again by that same factor, or you square that factor, and that's what happens to the area. So if I double this, it's 4 times. If I half it, it's a 4th time. 1/2 times 1/2 is 1/4. Wow, what an interesting concept. We're going to now apply that to a couple of different other things. Let's take a look at these 2 rectangles. We want to find the scale factor of the smaller rectangle to the bigger rectangle. What's happening? We want to know what's going on going from smaller to bigger. If I'm going from smaller to bigger, well, I have to look at what's happening as I go from one to another. I'm looking at things that are alike. 10 going to 15 and 16 going to 24. What happens? How does it change? Remember our how do things change? So that's really what we're looking at. When we start with 10 and it goes to 15, remember back, this was X, this was Y, and when we write that as a ratio, we will write it as Y over X, which means 15 to 10. Now 15 to 10 is an improper fraction. We can simplify it in a couple of different ways. First of all, we could say, well, you know, both of those are divisible by 5, and so if I divide them both by 5, I'm going to get 3/2. 3/2 is a ratio of 3 to 2, but if I want it to be a scale factor, I need to know what I'm multiplying by. So I can either say it's 3/2 or 1.5. Now, if that works for that, it should also work for 16 and 24. If I do 16 is to 24, and I write that as 24 to 16, X is to Y, we do our ratio always Y over X, and we notice something interesting, I hope, here, that this, they're both divisible by 8, which also is 3 to 2, or 1.5. So the scale factor here, going from our little rectangle to our bigger rectangle, is 1.5. You can find it regardless of what sides you use. They're corresponding. It's going to get bigger the same amount. Now, if we were to go the other way, we'd be getting smaller by the same amount. Okay? If we're looking at area, remember, area is multiplying the side by the side. So on our original, this would be 10 times 16. That's easy. 10 by 16 is going to be 160. Our other one is 15 by 24. Now for that, you might need to get out a calculator and multiply 15 times 24. When you do, you end up getting, what is that, 360. I want to make a comparison of that. What is the area scale factor? Well, I'm going from 160 to 360. If I write that as a ratio in fraction form, x is to y, I'm still going to put my y value over my x value. And hopefully you guys can notice that there are some very common factors in there. First of all, they're both divisible by 10, which means that I can make this 36 and this 16. And I hope you all recognize that they also are now divisible by 4. And if I divide them by 4, this is going to become, do this a little bit different color, 9/4. Or, if I simplify that, that's going to be 2 1/4. Now, we're working with fractions, but notice something. We said that if we take that amount and times it by itself, we will get this amount. That amount times itself will give us this amount. Let's see if that works. If I take my scale factor, which would affect size of sides and perimeter, and multiply it by itself, that would be 3/2 times 3/2, and amazingly that is 9/4. What? Yeah, because remember, area is affected by lengths going both directions. So it's affected this way as well as this way. It's squared, it's times itself. And we still would get 2 1/4. Now, this is a little bit different question. This question says, how many of the smaller rectangles fit inside the bigger rectangle? Now, we could trace the two rectangles and we could fit one in there and then start cutting up whatever's going to be left and making another one and then seeing what it is. But here's the secret. It has to do with area. This area fits into that area. How many? Oh, this area is 160. And if I divide it into 360, oh, wait a minute. Isn't that what that fraction is? It is. I can fit those in there. 2, oh, that's 320. And I get 40 left over, and if I put 40 over 160, that is going to be 2 1/4. So how many of a smaller thing fit into a larger thing? It's the scale factor of area. It's the scale factor of the area. Wow, mind-blowing. Okay, so let's take a look at a pentagon. Well, we know it works with triangles. Oh, we know it works with rectangles. And guess what? Pentagons are just comprised of triangles and rectangles. So if it works for triangles and it works for rectangles, 3 sides, 4 sides, 8, 5 sides, same thing's going to happen. So we want to know the scale factor of the smaller pentagon to the bigger pentagon. Well, if you look here, you'll notice that our smaller pentagon has a side length of 1.4 millimeters. It corresponds to a side length of 8.4 millimeters. We're looking at what happened to our smaller one to make it our bigger one. We can do a ratio, or we can simply divide, because that's what happens when we make a ratio. When we make our ratio, remember, even though we're looking at small to big, our original is on the bottom and our new is on the top. And so if we were to do this as a ratio of the new one to the original, and this is going back using stuff from previous lessons, our new one would be 8.4 millimeters to 1.4 millimeters. Now, since they're decimals, basically the easiest thing we would do is grab a calculator and look at how many of 1.4 fits into 8.4. So if you do that on your calculator and you say, I'm trying to figure out 8.4 divided by 1.4, you end up getting the magic number of 6. So our scale factor is 6. Everything here was multiplied by 6. What about the area scale factor? Okay, we've talked about that now in 3 different scenarios. We saw that if our scale factor was 2, then the area scale factor was 4. We saw when it was 1 1/2 or 3/2, the scale factor was 2 1/4 or 9/4. It was the scale factor multiplied by itself. So the area scale factor is going to be 36, because 6 times 6 equals 36, the number times itself. And so if you're asked, how many of the little pentagons fit inside the big pentagon? Well, we don't want to sit there and trying to cut the shapes and fit them in. That would be crazy. Instead, we know the area scale factor. Well, guess how many are going to fit? 36. Because you're talking area, not just one direction of length or width, but you're talking the whole area. And there you have it. A little bit of comparison for scale factor of lengths versus scale factor of area. And remember, perimeter is the sum of the lengths. It's going to be the same scale factor for perimeter as it is for the length sides changing. But area is sides by sides, so it's going to be whatever the scale factor is one direction multiplied by itself. So there you have it for today. How to look at scale factor and how many smaller figures will fit inside a larger figure. If you have any questions, feel free to go back, replay this video, pause, look at what's going on, contact your teachers if you have questions, and have fun with scale factor.